Okay, so so today, provided we can see something on the slides here, I'm going to talk some about reasoning about knowledge in distributed systems, which is in some ways a complementary approach to topology, or handles a few things that topology doesn't handle in the same way, and allows us to do certain things differently. The two lectures, or the 2 hours, will actually be 2 lectures. One is along the lines of the very early work that I was involved in my thesis and that started this topic. And this is joint with Joe Halpern. And the second lecture will be an illustration of one of the latest works in the field, sort of showing what we can do using knowledge. And this is a precursor to the course that I'm planning to give next semester in EE. There's a book called Reasoning About Knowledge. This is 500 pages covering the first 10 or 12 years, and it's been 25. So I'm not going to cover everything that's there, just going to give a taste of a few of the notions. And, okay. And now we can start with the technical. So the term knowledge actually has been used, is very commonly used in natural language, has been used for thousands of years, and it really means different things to different people, and it refers to different concepts in different situations. So, for example, I can say, can you see this? I don't know how we get this yellow and why it's so small, but so, for example, I can say that I know that I'm giving a lecture right now. Okay, that's a reasonable thing to say. Saying that I knew you would say something, I knew you would say to someone on the way, uses the same word in a slightly different meaning. It's probably I expected, I believed, I know who stole my wallet. Possibly I'm convinced that whoever I suspect did it, but I might say this even if I didn't see the thief actually do this. A dog knows who its owner is. Well, a dog might know, and we say reasonably that the dog knows its owner, but in most of, say, in these cases, you can challenge me. You can say, okay, you only know something if you can, say it explicitly. Well, will the dog say explicitly who its owner is? Probably not in English. Another place where we can say that you know something is, suppose I have an encrypted message that Morris gave me to hand to someone else. If it's computationally encrypted, then there's only one decryption. There's only one possible thing that's in there. Am I allowed to say that I know the contents of the message, even if I haven't computed it? Obviously I can. I can sit down, spend 100 years, try all the combinations, and find it. So these are just examples of different notions of knowledge, and there are lots of questions of what is knowledge. Now, this is more a matter for philosophy, not for us. And questions such as, does knowledge entail truth? If you know something, does it have to be true? Well, for us, the answer in this case will be yes. Should the knower be aware of the knowledge? So I can say that you know who stole your wallet, Morris, even though, think about it. You know who stole your wallet, okay? So would it be, if you say, yes, I remember that guy, then did you no, well, there's an interpretation under which you did and one under which you didn't. Here again, did I know the contents of the encrypted message? Well, there's information theoretically, yes. If you want to take computation into account, then the answer would be no. In general, knowledge has been studied in philosophy for thousands of years. It's a very common topic in linguistics. Aumann, the Nobel Prize winner in economics, introduced rigorous modeling of knowledge into economics in 1976. McCarthy to AI in 75. And in the early 80s, we started work on knowledge in distributed systems, and roughly at the same time, or slightly after, there was work on zero knowledge and things like that in cryptography. Now, I'm going to be focusing on knowledge in distributed systems and illustrate some of the notions that we talk about. And I see that it's going to be challenging with these with this projector. In any case, we're going to look at a particular interpretation of knowledge, which will be essentially, you know something if the information you have implies it must be true. No computation needs to be involved under this interpretation. Typically, I would know anything that follows from the information that I have at hand. And one basic property that all of these notions of knowledge or all these fields assume of knowledge is what's called the knowledge axiom, which says ki phi implies phi. If I knows phi, phi must be true. By the way, the notions used in game theory and the ones we use are essentially the same notions. So why apply knowledge to distributed computing? Well, essentially, distributed computing is concerned with questions such as, have messages arrived, have registered been written when and in what order, do events happen, which processes move, which fail, and what relevant events occur at different sites, at your own site and at other sites. And basically, I think Morris mentioned this earlier, a process acts only based on its local information. And this local information contains only partial information about the state of the world. And we often view communication as an operation that changes the state of knowledge of the system. And that'll be a basic theme here. Now, ever since there was communication and distributed computing, anyone writing a protocol talks about knowledge all the time. As long as this node has not received an acknowledgement, it doesn't know that the other node is ready to use the protocol, etc. So whenever you do anything with a number of sites, number of robots, a number of nodes in a network, you talk about knowledge all the time. The point here is that formalizing the notion of knowledge allows finer analysis of various problems. That's what I'm going to illustrate in, well, I guess in both talks. That's what I hope to illustrate. So the basic thesis is that reasoning about knowledge is a useful way of approaching issues in distributed computing. And I'm taking what has become a classical example in this area, which is not an example from distributed computing, but the purpose of this example is to illustrate some of the subtleties and the fine points of reasoning about knowledge. So the puzzle is called the Muddy Children puzzle, and it goes as follows. We have n children playing in the mud. After a while, k of them become dirty. Dirty in this case means that they have mud on their forehead. You see these guys, these K guys here? They do, the others are clean. And the assumption is that they're wizards, as you can see. They're floppy disks. So they're collectors as well. And so they're perfect reasoners. Anything we can figure out, they can, any puzzle we can give them, they can solve correctly. And moreover, in this picture, there is a father that is truthful and that they all trust. So the father comes by and he sees that some of the children are dirty, and he remembers a puzzle from way back, and he says, these are whiz kids, so let's ask them the puzzle. He goes and he asks them whether they know they're dirty. Does any of you know that you're dirty? And the protocol here is he takes off his hat. They're supposed to say yes or no on the little note, put it in the hat, and then the father announces the answer. So he asks them, well, does any of you know that you're dirty? And they all say no. Oh boy, this here is no. N of them all say no. Then he says, well, you all said no. Does any of you know now that you're dirty? And again, they all say no. And then he says, well, you all said no. Does any of you know that you're dirty? And now they all say no. And then he continues and goes off the slide. And then he says, oh, but, probably have a temperature. I'm not feeling well. Something didn't work out as I intended. So this happens on day 1. And he says, if this happens again, I'll do something different on day 2. So essentially, there's there's a formal claim here that on day 1, in fact, this is just a recap of the situation, the father repeatedly asks, do you know that you're dirty? All of you said no. Do you know now? And they all repeatedly say no forever. And the proof, and there's actually a claim that this is in fact the case. Very simple proof. Well, we prove by induction on the round number that they'll always say no. Well, in the first case, in the first round, I look around. I don't see my own forehead, so obviously I don't know if I'm dirty. Okay? And in general, assuming inductively that in all rounds up to round m, where m now is greater than 1, everyone said no, regardless of whether there were k or k minus 1 muddy children. For all k, the claim is that for all k, they'll always say no. So that means that whether there are actually k, I see 2 muddy children, and I'm the third one, but even if I basically am unsure whether I see 2 muddy foreheads. I'm not sure whether I'm the third or whether 2 is all there is. If 2 is all there is, then in the first m minus 1 rounds, everyone would say no. And if 3 are dirty, then again, I would see exactly the same. So I can't tell these 2 situations apart. And so I don't know, after 5 rounds, I don't know if I'm dirty or not. So I say no, and by induction, this is true for all m. Okay, that's why we go off the slide. And fine. Now, this was supposed to be, okay. So come day 2, the same situation arrives. And now the father uses sort of the same slide, but he starts out saying, at least one of your foreheads is muddy. Okay, at least one of you has a muddy forehead. And then he says, well, do you know that you're dirty? And as you saw, the animation didn't work, so they all say no. And he asks, do you know you're dirty? They all say no. He asks it again. They all say no. And he continues until at some point, they all say yes. Okay? So that's the difference between day 1 and day 2 is that in day 1, he starts out saying, well, at least one of you is dirty. No, saying something that's completely obvious because everybody knew this even before he said it. And yet, at some point in this case, all the dirty children would discover that they're dirty. Okay? So let's see why this is true. That's a recap. Claim on day 2, the K dirty children will answer yes to the kth, in the kth round, to the kth question. Why is this true? Well, by induction on K this time. Okay, on the number of muddy children. If there are K muddy children, then they all answer yes to question number K. If K is 1, of course, the muddy child, I look at you, you're all clean. And then comes father, Morris is here, father in this case, saying one of you is dirty, and they say, okay, all of you are clean. Trusted father says someone's dirty, so I must be dirty. So if there's one, obviously the single muddy child would say that he's dirty. Now, assume that the claim holds for K minus 1, or for everything up to K minus 1, and K is more than 1. Well, in this case, here I am seeing 2 muddy foreheads. And again, I'm uncertain about whether there are 2 or 3, whether I'm dirty or not. If I'm dirty, there are 3. But, I'm a perfect reasoner. So I say, if only the 2 muddy children that I see are dirty, then they'll say that they're dirty in round 2. That's sort of by induction. So in the second round, I say, I don't know if I'm dirty. I've seen, the first round, nobody knew, that's fine. The second round, I still, it's possible from my point of view that I'm clean. And the same is true of the other 2 muddy children. So we all say no in the second round. But then come the third round, we realize that it can't be that they're only K minus 1. I can't be clean, because if I was clean, then the other dirty children would have said yes in the previous round. Once they say no, I discover that I'm dirty, and then I say yes in round K. Okay? So, seeing that nobody said yes in the previous round, I say yes, and I'm done, and the proof is done. Okay. So these are all, you came here from the math seminar. This is as low as you can go, right? I mean, this is very simple. But there's a question here that is maybe non-trivial. Look at the difference between day 1 and day 2. In day 2, the father comes and he says something that's completely obvious. And suddenly, there's so this is saying the obvious here. How does saying the obvious make a substantial difference? In day 1, they couldn't figure out whether they're dirty. In day 2, someone comes around, says something that's completely obvious, and suddenly it makes a world of a difference. So,
Why is obvious? Maybe no one.
No, but there are 3. Suppose there are 12. Okay, 12 muddy children among 100. Suppose this was more popular. So I was one of 12. Father comes and says there is a muddy child. So, okay, so I agree definitely that for the case of K minus 1, it matters. And clearly this proof fails in day 1 because we don't have the basis, right? The basis of the induction fails. But saying that the basis of the induction fails is a technical reason why this proof doesn't work there. But in a deeper sense, what?
Why is it just technical?
No, so what is it? So suppose there are 12 muddy children, and one thing will not work if you don't say something that's obvious. So you come here and you say there's a door here. Suddenly everyone can do something. you know. And it's not that they have to go to the door. Then you ask them the same thing, they're supposed to answer the same questions, and you said something that, here's a door, and suddenly they can do something. Okay, so the point is that there are various subtle aspects of knowledge that make a difference between day 1 and day 2. I'm wondering if I move the slides over to, if I move by USB there, whether life would be better or not. Okay, so in order to get a better grip at the difference between the two days, or the epistemically, in terms of knowledge, what's going on here, let's go and just make, can you see these things? I mean, at least the blue and, okay. So let's take a bit of notation of what's called the logic of knowledge, and I'll fill in the things that are hard to see. So let's write Ka phi for child A knows fact phi. Okay? And we can write Kb Ka phi to say that B knows that A knows phi, because if we use knowledge operators in this sense, then Ka phi itself is already a fact. So for any fact, knowing a fact is also a fact. Then we can talk about, we can talk about facts. We can talk about knowing a fact, knowing that someone knows a fact. We can, of course, add propositional logic and whatever. A higher level of knowledge is for everybody to know phi. So I would claim that one reason why we could say that the father's statement was obvious was he said something that everybody knew. Okay? Some saw the 3 dirty children and some saw 2, but everybody knew that there was a muddy child. And yet, when the father, after the father said this, there's a difference. So we can talk about everybody knowing a fact, and we can also talk about everybody knowing that everybody knows a fact, and we can iterate everybody knowing any number of times. So everybody knows to 100 says everybody knows that everybody knows 100 times. It's not completely clear whether there should be a difference between everybody knows that everybody knows 9 deep and everybody knows that everybody knows 10 deep, but we might see that a little later. And then in the title there was knowledge and common knowledge in a distributed environment, title of this talk. Common knowledge is taken to be the infinite conjunction. Everybody knows something, and everybody knows that everybody knows it, and everybody knows that everybody knows that everybody knows it, and so on. Everybody knows to the m for all m. Okay? So that's sort of the limit of a nested everybody knows. That's called common knowledge, and plays a more interesting role than one might I think, and this is one of the things that we'll see in this talk. So now, yes?
Common knowledge phi, C phi.
Yes?
Does it have to contain phi itself, or only everything knows, only if phi? Should we start?
If it knows phi, then phi must be true.
Yeah, so if knowledge satisfies the knowledge axiom, then phi would be true already. And there's a very similar definition of common belief, and then it makes sense to drop phi there, because belief is, when you believe something, it doesn't have to be true, and so that's why this is, so this form, the same form works here and there, and that's why the phi is not there, but in our case. Okay, so now we started off from the idea of, well, an individual could know something, and we'll see more about that later, so I haven't defined it. When does a group know a fact? Well, you could say that this group knows how to get to a certain restaurant in Haifa if one of us knows how to get there. Or you could say the group knows if everybody knows. If each of us needing to go there could go there. Or maybe you could say, well, the group really, for the group really to know, everybody needs to know that everybody knows, or any of these. Or maybe if phi is common knowledge, then the group really knows. And these are different flavors of the knowledge of groups. In fact, we discuss, and it makes sense to discuss, even a weaker. So you can see here a hierarchy of states of knowledge. Somebody in the group knows phi, everybody knows that everybody knows, all the way up to common knowledge. These are all strengthenings. And it also makes sense to talk about distributed knowledge. So maybe we know how to get to the restaurant. If I know how to get to the bus, and somebody knows how to get from the bus station off in Hadar to this restaurant. Okay? So even if I know part of, if I know that psi implies phi, and you know psi, then together we have distributed knowledge of.
Weaker than the first.
That's weaker even than the first. That's even here. And one of the views that we have, or that we suggested early on, was that communication in part can be viewed as the act of moving the state of knowledge up this hierarchy. So this hierarchy goes up. There's like trees go, up this direction, and we could think of communication as climbing up the hierarchy. Okay. Now, we come back from the detour to the muddy children, and we can basically prove, and this is now I'm waving hands, that solving the muddy children requires k levels of everybody knowing that everybody knows. Psi was one of us has a dirty forehead, and they also need to know that they all know that everyone's a perfect reasoner. Because for me to know that I'm dirty after you didn't say something in the first round, it's not enough for you to be, what?
Don't you only need K minus 1 for the rest?
We need K.
You need K for all of them?
We need K of all of these. You need to go K levels of the induction. And maybe the others K minus 1. Let's assume. Okay, the point is that it's not enough for, if there are only two muddy children, it's not enough that the other muddy child would be a perfect reasoner and could tell from the father's statement that they're dirty. I won't be able to conclude that I'm dirty based on the silence of the other child, unless I know that they're bright enough to figure out from the father's statement and the fact that everyone's clean, that they're dirty if I were clean. Okay, so it's not enough for everyone to be a perfect reasoner. Everybody needs to know that everybody knows that, and so on, and that they all hear the father, and that they all see all the foreheads, and they all trust the father, etc. Okay, the point is that, and you can show that when there are K-muddy children, K-muddy foreheads, then everybody knows that everybody knows for K minus 1 levels holds of the muddy forehead. Okay? Think of it. If I'm the only muddy child, then everybody knows to the 0 holds. I mean, not everybody knows, because I don't. Okay, if it's just Morris and me, now Morris is back down to one of us kids, then he knows there's a muddy child, and I know, so everybody knows there's a muddy child, but I think it might be just him, so we don't have everybody knows to the K. K is 2 in this case. Okay? So if we only had K, if we just did have K levels, then even on day 1, it would be able, they could solve the problem. But in fact, there are just K minus 1 levels, at least, of knowledge of this. And the other things we assume sort of are common knowledge, so it's not that critical. And the point is that, okay, that's psi was, at least one of us is muddy, And if we have k muddy children, then everybody knows that the k minus 1 does hold. When the father says one of your foreheads is muddy, then this fact becomes common knowledge. Okay? Because it's a public announcement. Everyone hears the father. Everyone knows this. But everyone can see that everyone else hears the father. So everybody knows that everybody knows this, and so on. So we can prove by induction that everybody knows. So a public statement inherently implies everyone hears it. And because of this, it implies that everyone sees there was a public statement, so everybody knows that everybody knows it, and so on. We can prove inductively that everybody knows holds for all levels. So to the power 1,000, 1,000,000, and so on. And in particular, it gives us everybody knows to the k, which we didn't have initially. Okay? So, first of all, this example shows us that there is a difference between everybody knows to the k and everybody knows to the k minus 1. That's what the not equal here stands for. Sorry about the red. So everybody knows to the k is essentially different from everybody knows to the k minus 1. But the public statement here gave us common knowledge. And common knowledge was, in particular, gave us everybody knows to the k. And that was, so in this sense, the knowledge-based analysis, A shows us that there are subtle differences. There is a difference between everybody knows to the 9 and everybody knows to the 10. Doesn't apply in all cases, but when k is 10, this matters. And in fact, there are actions that create common knowledge, and those give us, and one instance is the muddy children puzzle or a public announcement as here. Okay, I want to look at a second example. Well, any questions about this?
Wasn't this originally about cheating husbands?
So the cheating wives, not cheating husbands. Cheating husbands was another take that we took on it, but this was originally called the cheating wives puzzle, which goes back, I think, to the 40s or whatever. And muddy children is the non-sexist version. And then the second flip was a paper we once wrote about the cheating husbands in a matriarchal. So, and cheating wives, what was a story, the same puzzle was that in Baghdad, the Pesha discovers that there are cheating wives, and he decides to get rid of this. So he calls all the men to the city square, and he says, at least one of you has a cheating wife. And if you discover that your wife is cheating, no one, you all know about all the other wives. None of you knows about his own wife. And you shouldn't talk about this with anyone, but should you discover that you have that your wife is cheating, you have to hang her at midnight in the town square. And then a number of days go by with quiet, and then suddenly there cries and shouts. So that was the so this is the politically correct version with the muddy children. And okay, but this was what I was after in the sense of saying something obvious, making a statement, saying that I am head of the mafia, might, saying this is one thing, but writing that, the president is a rapist, okay, and then in the newspaper. Could be that everybody knew this before, but once, say a court says this officially, then it becomes common knowledge. It could be that I'd be very happy if everyone knew I was, head of the local mafia. I would have a parking spot. I would, be treated kindly in various places. But if it was written in black on the headlines of the newspaper, well, maybe I would be upset because it might have negative connotations. Before that, everyone knows this, but no one knows that they can really say that for sure or whatever. So That's a distinction between public announcement and not. And we'll go to a very famous problem in distributed computing called the coordinated attack problem, where we care about communication and coordination. This is a problem introduced by Jim Gray, who was a Turing Award winner, was lost at sea a couple of years ago, one of the greats of database and concurrency theory. And it goes as follows. We have two divisions that are located on opposite hills, and the enemy awaits in the valley between them. They communicate using messengers, which are very efficient and effective messengers, but they have to cross through enemy lines, and they can always be caught. And now one of the generals of one of the divisions discovers that the other division is on the other hill and wants to coordinate an attack. And they know that if both divisions attack together, they win. But if one of them attacks alone, it'll lose. So none of them is going to attack unless they attack simultaneously. The commander of the first division would like to coordinate an attack. They don't have an attack, pre-coordinated. And the question is, how are they going to do this? Or our actual question is, envisioning such situations, what protocol should we teach the officers in officers' course so that they'll be able to successfully coordinate such an attack? Well, here's a picture. We have the two generals. Each of them has a helper, just like Sancho Panza here. And this is the enemy. So, Don Quixote is here, and he sends a message saying, let's attack at dawn. Okay? Now the messenger is very good. He crosses the valley, gets to the other side, says, troops, we're attacking at dawn, prepare. But then his own helper says, wait, we can't attack. You know that Don Quixote is not going to attack unless he's sure that we're attacking as well. He said, yes, but he sent us a messenger. Of course, the messenger could have been lost along the way. So he says, what should I do? Well, of course, we have to send the messenger, or a fresh one, back with an acknowledgement. That's what acknowledgements are for. And right, you send a message, I send you an acknowledgement, I got your message, and so they do that. And Don Quixote now is relieved. His message arrived, and he tells his troops to prepare. We're attacking at dawn. But then Sancho Panza says, we can't attack at dawn because, the other guy, Nelson here, he's not sure whether his acknowledgement got to us. And he knows that if it didn't, we're not going to attack because we fear we're attacking alone. And so, what should we do? Well, we have to send back an acknowledgement saying, yes, your messenger arrived. And then the messenger arrives, and Nelson is now relieved. His act has arrived. And then his helper says, but they're wondering, they know if you don't get this acknowledgement, you think your acknowledgement didn't get there, and so you wouldn't be attacking. So what should I do? Well, he has to send an acknowledgement, and we see that we get back into the same situation as we go along, and this has a happy ending because they never attack, and there's ceasefire and peace breaks like in our area, and so the story has a happy ending. But the point is that
So miscommunication is not the reason for war, it's the reason for peace.
yes. So it says that if communication is not reliable and coordination has to be guaranteed, it has to happen simultaneously, so this was all introduced in order to describe how unreliable communication can cause problems in distributed databases. You have different databases, different sites, they all have to keep, maintain the same state and make the same updates. And if you insist on this, then, well, even on nights when all the messengers go through, you're never allowed to attack or to make an update. So you're never allowed to make progress. So in computing, this is worse news than maybe here. And in fact, Gray argued that there's no solution to the coordinated attack problem. So for every protocol, if the protocol satisfies the property that nobody ever attacks alone, by himself and loses, then in red, nobody ever attacks. Okay, so if you want to guarantee that there's no mistake, then you're guaranteed never to make any progress. And this is true even on nights in which all communication is possible. You're only worried that there could be problems with communication. So one thing we show in the work using knowledge is that, in fact, this can be explained and generalized considerably by way of reasoning about knowledge. And essentially, since attacking is a simultaneous action, because by now a literature showing that simultaneous actions are very closely related to common knowledge. If there's any action which I perform if and only if you do at all points, then when I'm performing it, I know that you're doing that as well. Okay, the protocol guarantees that I only do this if you're doing this at the same time. Then when I do this, I know that you're doing it, or I know that we're both doing it, and same with you. So when we're doing it, inherently, it's a public event, just like the public announcement was before. And so when we're attacking, it must be common knowledge that we're attacking. Okay, if you have a protocol that satisfies that I never talk alone, like you never walk alone, what is this, Liverpool or whatever. If I never attack alone, I always attack with the other side, then when we attack, it must be common knowledge that we're attacking. And if we assume that we didn't have a plan to attack originally, we need to coordinate this attack, then this assumption basically boils down. One way to formalize it is to say, well, in the absence of any successful communication, if no message is delivered, then we don't attack. Okay? I mean, if we can attack even if none of us receives a message from anyone else, then one could argue that we had a we had a plan to attack. So if it's not coordinated, then when we attack, it must be common knowledge that at least one message was delivered. Okay? And what we can prove is that when communication is unreliable, non-trivial facts, for example, the fact that at least one message has been delivered, is never common knowledge. So even after 1,000 messages have gone through, and regardless of whether the protocol was the one we saw between Sancho Panza and Nelson of sending an act, regardless of the protocol, you cannot get common knowledge of any non-trivial fact. For example, of message has been delivered in a system when communication is not reliable, or in a system in which communication is asynchronous, so we don't know the pace. And as a result, coordinated attack is unsolvable in lots of contexts. For example, if messages can be lost, or if there's sufficient uncertainty as to how long messages take. And it's not only coordinated attack, but any simultaneous events that depend on at least one message being delivered can't be coordinated if communication is unreliable. And the funny thing here is that all of this happens because basically because of paranoia. You have a night where 1,000 messages go across, nothing, there's been no communication failure, but you assume the possibility of communication failure and you're in trouble. This is very close in spirit to some of the things that Morris has been talking about in terms of failures. The proofs that Morris was giving in the last couple of lessons went for runs in which no failures happened. Now, everyone worked in lockstep, and still the possibility of things going wrong was what happened, what created trouble. Okay, so I'll start. Let's see, how are we doing on time? Okay. I'll spend 5 more minutes and we'll take the break. Yeah, I guess we started a bit late. Okay, so the kinds of knowledge-based analyses that we do in this area is analyzing a concrete protocol in terms of knowledge. So you have a particular protocol, alternating bit or something, and you can ask, well, what states of knowledge arise here? You can ask, given a problem, what states of knowledge are necessary, need to be attained in order to solve this problem. And we'll see an example of this in the next hour. We can analyze a state of knowledge that are attainable in a given setting, in the synchronous setting, in the asynchronous setting, when communication is not reliable, where there's uncertainty as to what transmission times on channels are, and so on. And combining all of the above, we can sometimes prove that a protocol does or doesn't solve a certain problem, or does this optimally in a given context, or maybe some problems are unsolvable. As I said, we'll see an example in the next hour. Okay, I'll skip this slide. See, I'm missing. Okay, good. So we'll take a break now. There are 3 slides of sort of modeling knowledge that somehow were not in this version, and I'll find for after the break. And then after the break, I'm going to talk about so this is work from 25 years ago. I'll talk about work from the last year, about applying knowledge to understand the role of time in coordination in distributed systems. So the question is, how do you analyze what types of coordination are possible when you have information about how long messages take in transit? Okay, take a break now. If there are questions, I'll answer those, but